We started in graph 24.9 with a signaling game in which beliefs by the receiver didn't really matter. Once the receiver received the signal from the sender, he didn't care whether the sender was a type 1 or a type 2 sender. His actions, his best response, was clear. In graph 24.10, we then changed the game just a little bit, and we found that in this new game, a pooling equilibrium in which the two sender types send the same signal could only survive as an equilibrium if the receiver had certain beliefs off the equilibrium path. In other words, certain beliefs in the event that the action that never gets played in equilibrium by the sender were to be played. But nowhere in either the pooling or the separating equilibrium we identified in the game in graph 24.10 did the probability rho play any role, the probability with which nature assigns a type 1 to the sender. We'll change the game a little bit more here, and we'll see an example where rho begins to matter. We begin with the game tree from graph 24.10. Notice that if the sender sends a signal left, the receiver doesn't care about what type the sender is, because whatever type the sender is, the best response to left for the receiver is to go up. If the sender, on the other hand, sends right, then the receiver does care which type the sender is, because if the sender is of type 1, the best response for the receiver is to go up, whereas if the sender is of type 2, the best response for the receiver is to go down. Beliefs by the receiver therefore begin to matter when the action that's a best response for the receiver depends on what type the sender is. We'll next consider a new game in which we change the magenta 20 in the upper left of the game tree to a magenta 10. In other words, we change the payoff that the receiver receives if the sender is of type 1 and sends a signal of left, and the receiver responds with the action up. Before it was 20, now the payoff is 10. In this new game, the receiver now cares what type the sender was if the sender sent the signal left. If the sender was a type 1, then the best response for the receiver is to go down, whereas if the sender was of type 2, the best response for the receiver is to go up. Suppose then that the receiver believes that the sender is a type 1 with probability gamma if the sender has just sent the signal left. The expected payoff from going up after observing the signal left is then 10 gamma plus 20 times 1 minus gamma, whereas the expected payoff of going down after receiving the signal left is 15, because that is the payoff from going down after a left signal, regardless of what type the sender is. 10 gamma plus 20 times 1 minus gamma is greater than 15 only if gamma is less than 0.5. The best response to receiving a signal left is for the receiver then to go up if gamma is less than 0.5 and to go down if gamma is greater than 0.5. On the right side of the game tree, we'll again let beliefs be denoted by delta. In particular, delta is the probability that the receiver places on the sender being a type 1 if the right signal has been received. Since the right side of the game tree is unchanged from graph 24.10, the same reasoning we used there will apply here. The best response for the receiver to receiving a right signal will be to play up if delta is greater than 0.5 and down if delta is less than 0.5. We can first check to see if the pooling strategy of playing left-left on the sender's part can still be part of a perfect Bayesian-Nash equilibrium. First note that the receiver, while not knowing what type is sending the signal left under such a strategy, does know from the beginning of the game the probability rho with which nature has assigned type 1 to the sender. Since, under the pooling strategy, the sender is revealing no information by sending the signal left, the beliefs on the part of the receiver cannot have changed from the beginning of the game, since no new information has been revealed. Thus, it must be that under such a pooling strategy, gamma is equal to rho. Thus, if rho is greater than 0.5, gamma is greater than 0.5, and we just concluded that if gamma is greater than 0.5, the receiver will best respond to a left signal by going down. But if part of the receiver strategy is to go down after observing a signal left, then a sender of type 1 can do better by deviating from the pooling strategy and going right. This is because by going right, sender 1 will get either a payoff of 15 or 5, whereas by going left, with the receiver following by going down, the sender's payoff will be 0. The pooling strategy, left-left, can therefore not be sustained in a perfect Bayesian-Nash equilibrium if rho is greater than 0.5. But if rho is less than 0.5, gamma is less than 0.5, and we've concluded before that the best response for the receiver is then to follow a left signal by going up. In that case, the pooling strategy of going left-left can indeed be part of a perfect Bayesian-Nash equilibrium, where the beliefs on the left side of the game tree are gamma equal to rho, and the beliefs on the right side of the game tree have to be delta less than 0.5 for the same reasons as in graph 24.10. The pooling equilibrium, that's a perfect Bayesian-Nash equilibrium, is then for the sender to play left-left, for the receiver to play up-down, and for the beliefs to be gamma equal to rho when rho is less than 0.5, and for delta to be less than 0.5 as well. Notice that as in graph 24.10, the action right is never played by a sender in equilibrium. Thus, since right is never actually observed, the beliefs that the receiver has in the event that right were to ever be observed can take any form, whereas the beliefs on the left side of the table, where the action left has been played by both types, have to correspond to the initial beliefs that the receiver had prior to the game beginning, because when both sender types send the same signal, no new information has been revealed to change the receiver's beliefs. In the previous segment, we argued that a pooling equilibrium in which the sender plays the same action regardless of what type she's been assigned can survive only if rho is less than 0.5. But a separating equilibrium in which the sender plays the strategy right-left can survive regardless of the value that rho takes. If that is the strategy that the sender adopts, going right if assigned type 1 and left if assigned type 2, then information has been revealed to the receiver, because only type 1s send the signal right and only type 2s send the signal left. As a result, the receiver will update his beliefs and will know that delta is equal to 1 and gamma is equal to 0. In other words, if a right signal has been received, the receiver knows that she's facing a type 1 sender, whereas if a left signal has been received, the receiver knows she's facing a type 2 sender. The receiver's best response is then to play up, up. And if the sender knows that the receiver will always go up, then it is indeed a best response for the sender to play right, left. The separating equilibrium is then right, left for the sender and up, up for the receiver, with the beliefs delta equal to 1 and gamma equal to 0.